Thank you all for being here so early in the morning. So my name's John Lynch. I'm a software developer at SideFX. In the past, I've done fluid stuff and ocean stuff and that kind of thing, and the last few years have been, I've been one of the main developers on the Vellum solver. So today we're going to talk about improvements for 19.5, particularly in the soft and rigid bodies. It was not a long development cycle for 19.5, so there's not a huge amount of stuff, so we're actually going to backtrack a little bit to 19 as well and show some things that got backported to 19 and that just were in 19 in the first place that are a little more obscure that people might not know about. So some of the improvements for tetrahedral constraints, basically we introduced a new model for scale and variance. Basically that just means that as you change resolution and change size on the tetrahedral bodies, that the material behavior stays the same. Honestly, this is how it always should have worked, and we sort of fixed it for 19. So this was actually important, well, for 19.5. This is important enough we actually backported to 19.0. We've added some optimizations when you have tetrahedral soft bodies along with sliding constraints. Both of these things are very important for muscles and organic sims. So we have a muscle tool set that's coming out, and various people, other studios and companies have been doing muscle sims with Vellum. Both of these things are really important when you're doing organic simulation. We'll sort of show why that is. We have a new technique for doing rigid bodies using grains. Grains have been around a while, and shape matching has been around a while, but we basically combined the two to give sort of a workflow that gives you kind of better physics and some better behavior, better performance. Generally, for rigid bodies in Vellum, you use it because you want to interact with other Vellum geometry. You want the rigid bodies to bounce off Vellum geometry or affect it in some way, or you want to do some certain special effects. Otherwise, just stick with Bullet. Bullet's tried and true, has been around forever, production proven, it's got tons of features. So this is not in any way a replacement for Bullet. It's just if you want to use rigid bodies, it's kind of a better way to do it within Vellum for 19.5. We'll talk about some new constraint tools, some things that you can do in the viewport. A couple of sort of more obscure Vellum fluid attributes. This is, again, stuff that just has been out there since 19, but not too many people know about. Again, the Vellum fluid is really for when you're interacting with other Vellum geometry, special effects. It's grid-free. There's no background grid, so you're not worried about domains or anything like that. But otherwise, you generally want to use FLIP. Again, it's just, if you're just doing a fluid simulation, you're generally going to want to use FLIP. It's been around forever. Again, production proven. And then we've got some sort of stupid Vellum tricks, which are just things people have asked me about over the last year or so, and just kind of clever, hopefully, possibly stupid examples of how to use Vellum in some interesting ways. And then hopefully we'll have time for some questions. So this is a technical live demo. It's kind of a masterclass style. There is some terrible programmer art ahead. It's all boxes and Houdini test geometry. I apologize to all the artists in the audience. So it's not going to look pretty. Hopefully there will be interesting content to compensate. So to start off with the tetrahedral stretch constraints, they are what's called as rigid as possible constraints. So basically they're constraints on the tetrahedron that ignores rotations and it tries to minimize any stretch and shear. They've been around since 18.0. The reason they're better than sort of the 17.0 version of Vellum is they're a constraint on the entire shape of the tetrahedron rather than just springs along the edges. So they can't invert. They just generally have better behavior. The new scale invariant ARAP model just kind of fixes some problems with the previous model that made it so that it wasn't consistent across resolutions, and you get better handling of mass and scale. This is pretty important because both, you want to be able to work at low resolution, use a stiffness setting, do some simulations, and then maybe go up to higher resolution. Or you might use adaptive tetrahedralization in a muscle. So you might have areas of the muscle that are curved that have lots of very small tetrahedra, and then larger flat areas that use larger tetrahedra, and they should all behave the same way. And that finally does this. As I said, it was important enough because we've had muscles in beta to backport this to 19. So that's actually been there a while. In 19, it's now the new default in 19.5. This correction gets it closer to the FEM solver, which we'll look at. There's a new static topology option, which just speeds some things up. And all of this combines to make for improved simulation of muscles and organic material. So let's switch into Houdini. So here's a very, very basic, as I said, lots of boxes and programmer art. And if we hit play on this, we're just going to see this is a Vellum soft body. It just sort of stretches and then falls to the ground and looks, you know, soft body-ish. So over here is actually an FEM solver, and it's basically set up to do the exact same thing. And the stiffness is set very close. It's actually 25% higher than the Vellum, but it's very close. And otherwise, it's set to use the same, you know, second order integration, 5 substeps. So they're basically the exact same settings. And if we look at both of these at the same time, you'll notice they get roughly the same behavior, which is kind of what we're going for. The FEM solver is maybe a little bit stiffer, but the idea is that the FEM solver has a stable Neo-Hookean model. It's very accurate. As you can see under collisions, it slows down a bit, but we're basically trying to get closer to that behavior with Vellum. And then more importantly, I cashed out a bunch of different resolutions. So this goes from sort of very low resolution here to high resolution here. All the yellow ones are the Vellum and all the green are the FEM. And the idea is just that they generally look qualitatively the same. So as you change resolutions, the material behavior stays similar. And if we look at sort of from the kind of front on, you'll see they sort of, as they're actually stretching a little bit further because they have more degrees of freedom as they get to higher resolution. But if you look at them from kind of both sides, they're behaving generally very similar. And that's pretty much what we want from, you know, your soft body simulation. So this is just, this shows up here on this, right here, this scale invariant ARAB model here. So these ones that existed before, generally, we don't recommend using them anymore. So even if you're in, you know, this is only the default in 19.5 because of backward compatibility reasons. But if you're doing anything new, any new simulations, we generally recommend using this model. It's more accurate, it's better. So that's just showing sort of the more accurate model. The other thing that has changed is, so this is more boxes, but this is a simulation that shows kind of what happens in a typical muscle simulation. So we've got 2 tetrahedral soft bodies here. They've got a bunch of tetrahedral stretch constraints and a bunch of tetrahedral fiber constraints. And if you'll notice when they're turning red here, it's actually the fibers are contracting. So they're contracting sort of across the x-axis here. And then the soft bodies are sliding against each other. So this is, in a typical muscle simulation, you'll have soft bodies, they'll be having some sort of activation, muscle activation, and then sliding, and the sliding is emulating like connective tissue of some sort. So this is fine. This all looks pretty good and everything. But as you move to sort of higher resolutions, so let's look at an actual live solve of this. So this is, we're going to make this bigger. So we've got 8 of these, which is about, I'm going to right-click on this. So you see it's about, the tetrahedrons here represent constraints. So there are actually almost 1 million constraints here. And if we, this stitch constraint here this is the sliding one. So if we turn off sliding for a second and hit play, you're getting about a second a frame for 1 million constraints, which is pretty good. The problem is we don't have any sliding happening. You can sort of see the muscles are kind of pulling each other without sliding as they pull apart, which is not really the look we're going for. So we're going to turn on sliding, but I'm going to go to the performance monitor and turn this on real quick. And we're going to take one step. And this, generally, if you're ever benchmarking any sim, you want to step once and then step again. Oops, I think I'd left something on that I did not mean to leave on. Sorry. Yeah, that was supposed to be supposed to be slower and then faster. So let's try that again. Okay, so sorry, so here we go. So we're going to do this one step, and what we're going to see is that we have a whole lot of time spent in what's called graph coloring. And graph coloring is basically, as the topology of the constraints change, which points are involved in each constraint can change as well. So as that sliding is happening, that topology of the constraint network is changing, and we have to re-graph color so that we can solve it very accurately on the GPU and solve it very efficiently on the GPU. So basically, any point in the simulation, we need to figure out all the constraints that are affecting it so we can solve it in parallel. So we need to regraph color whenever that changes, which is what happens when you have sliding going on. So if you notice, we're spending very little time in the actual, like the constraint update, for instance, but this graph color constraints here is spending 5 seconds a frame, which is a lot. So in 19.5, there's this new option where basically you can say, if I sort of promise that I'm not changing the topology of the constraints, I'm not going to delete any, I'm not going to add any new ones, then both on the tetrahedral stretch and the tetrahedral fiber, we can set this. And then if we step 1 frame and then turn on the performance monitor, and we'll see this goes down, the graph color goes down to about 0.8 seconds. So it's several times faster. And this happens again a lot in muscle simulations. What happens is we're actually storing the graph coloring value on the constraints. So it's got sort of just an extra attribute that gets reused. So it's doing an incremental update basically of this. And it just gets a lot faster. So, you know, saving whatever that is, 4 or 5 seconds a frame really adds up. So it's a nice optimization. It's important for things like cloth. If you have very dense cloth and also sliding constraints, this can also have an effect. Tetrahedra are the hardest to graph color. It takes the longest. There's 1 million of these. Any point can be affected like 40 by like 40 constraints, so it's a hard graph coloring problem. So it's most evident in like muscle sims like this, but it can be important in cloth and stuff like that, so it's worth kind of looking at. One other point is all that's really happening is we're putting, if you see this where it says prim groups here, there's one called __ static, and we're just putting the constraints into that group. If you know that you've got 10 Vellum constraint SOPs, you can also just group them yourself, which is what this does. This is basically just saying anything that isn't a sliding constraint, put it into the static group. This says equals all but sliding stitch. So just another way of doing that. Okay, so let's go to the RBD stuff. Okay, so here we have our flip test geometry. We have, I think, 100 of these. And let's say we wanted to simulate these as rigid bodies. So the obvious thing to do is put down an RBD bullet solver and, whoops, I'm not used to this mouse, sorry. Hook it up and give it a ground plane and hit play. And we get a rigid body sim, as you'd expect. Now, one thing to notice here is that as these collide, they're actually sort of not quite colliding exactly. They look like they're a little bit offset. And that's because if we visualize the collision shape, we're actually doing the convex hulls of these. So this is what's actually colliding inside bullet is convex hulls. Very common idea is that, you know, you don't actually do the convex, the polygonal representation when you're doing collisions in rigid bodies. You use the convex hull. So there's some ways to work around that, and one of the ways is if you do a VDB from polygons, and we're going to do this to 1, and so you make a little VDB out of it, and then you do VDB to spheres, and if we look at that, we get spheres that basically cover the shape of the little flip guy, and because it is basically doing sphere packing, so it's just packing spheres into this VDB, into this SDF here, the sign distance function that represents the body. So we can do something now with Vellum, because if you look at these look kind of like how we represent grains within Vellum. And we have the idea of shape match, which is basically we want to simulate the original shape of these points. We want to just keep the shape rigid while we do the simulation. So there's a new tool here called, Vellum configure grain pieces right here. And this basically does something very similar. It has this sphere packing setting here. And if we look at what we get out of this, we get basically a bunch of spheres around our little flip objects. And the lines here actually represent the fact that each one of these has a separate shape matching constraint. So if we look at this, I'm visualizing a piece attribute. So what this actually is doing is it's going through the connectivity of all these guys, creating a set of grains, giving them all a piece attribute, a unique piece attribute, and then setting up a shape match constraint. And then if we attach a solver, that is not what I wanted. Sorry. So we're going to attach a solver here and just change a couple of things. And we can actually turn off self-collision because all we're worried about here is actually grain collisions, which are sort of implicit. We play, and we get the same thing. We basically get a sort of what looks like a rigid simulation. So the important settings on the Vellum solver here are, under this advanced tab, we have, for grain collisions, we have ignore neighbors with the same name or piece. And so what that means is when we're looking at doing grain collisions, anything that has the same piece attribute value is ignored for grain collision. So all these things that are the same color basically will ignore each other. But as soon as they see a grain that's a different piece, a different color in this case, they'll collide with it. And then the other important thing, and this is also from 19, is this OpenCL neighbor search. So all of this, all the grain collisions are happening on the GPU, which makes them quite fast. And so we can turn these off, the self-collisions off. So these are just grain collisions. So that's all fine, but now you've just got a bunch of grain. So how do you make it get back to the original geometry? So there's now this new SOP called Vellum Transform Pieces, and what it'll do is actually look at the shape match constraints and the points and apply them to the original geometry. So, and it does it with velocity and angular velocity and all that kind of stuff. So as you render this, it gets proper motion blur, and you can instance this in Karma and do all sorts of stuff. So this is a very efficient way to have a lot of these. So the only thing that's not terribly efficient about this is, I don't know if you noticed, but like when I change the ISO value, it takes a second. And that's because it's actually looping over all of these pieces, and each one of these things, it's doing sphere packing separately on each of these pieces. So if you have a huge number of different shaped things, that's great, but if you have a bunch of that are identical like this, you actually only want to do this once. So there's actually, I'm sorry, I wanted to show one more thing, I'm sorry, real quick. So why, again, there's kind of the whole question of why would you do this? And you would do this because you want to interact with Vellum geometry. So in this case, I've got a little, and I want to turn back on self-collisions. Why did that not work? Oh, sorry, I messed up there. Let me try that again, sorry. That is also not what I meant to do. That is not happy. Yay, okay, success, finally. Okay, so this is why you would do that, is basically to just have the grains interacting, or the rigid bodies interacting with the, with some kind of Vellum geometry, like soft geometry like this. Let's turn that off. So anyway, that's why you do this, is just to get rigid bodies and Vellum of some type reacting, whatever it is. So the sort of more complicated setup for this is to actually, let's say we have a huge number of identical soft bodies here. And like this one again, we're going to give it a name. We're going to name it FLIP, and then do the same sort of grains plus shape match setup here. And then we're going to actually do a Vellum pack. And what this does is combines the constraints and the geometry into one packed primitive. And then we're going to make a ton of these. We're going to make, I think, 100 of these. And then we're going to merge them together with sort of the same thing, but we've done this with a pig head over here and with a squab over here, some more test geometry. And then when we do an unpack, so basically this turns it back into two streams of geometry and constraints, we have this enforced unique name attribute per instance. And so what we get out of this is a bunch of grains, and they all have a unique name. So if we in this case, we're going to visualize the name, you can see these all show up as different colors because each one has a unique name, and that's what this unpack is doing. So even though we created them with just a name of FLIP, we're adding this little sort of suffix on it to make it unique. And the RBD unpack has a similar workflow. And then if we solve this, where's the solver right there? So again, we get pretty good performance here, but again, this is just a grain sim. And if we, so we're doing something a little bit different though here. We're using Vellum transform pieces again, but we're actually using it in a mode where it outputs points with transforms. So these are just outputting little points, and if we look at the attributes on them, it has like orient and pivot, and basically these are all the things that you can send into a copy SOP, copy to point SOP. So that's what we're doing here. And again, we get quite good performance because this is just applying transforms to packed primitives basically. And so the one thing that we're doing that's a little bit different is we're actually taking our original name and we're stripping off that sort of suffix so that we have what's called just in this setup I'm calling a library name. And the library name is actually looking at the input here, and these are just the individual pieces of geometry. So that's like the pig head, and the pig head is named, if we look at these packed primitives, these are just their library name. So it's basically picking from a library of instances to copy onto those transform points. And again, there's a similar workflow to this in RBD, and the idea is just if you have thousands of these and you want to use 10 unique instances or 12 unique instances or something like that, you can sort of do it this way without having to do that sphere packing over 1,000 times or however many thousands times. So it's just a much more efficient way to work with that. This works well with a regular grain sim, not surprisingly. So if we this is just cached. So you can see it. This is just the same sort of objects interacting with real grains, and of course this works well because if we look at the actual output, this is just grain sim. So the other thing you can do with this is if we take those same packed geometries, but we don't create a ton of them, we're just creating, and what we're going to do here is actually create emitters. So we're creating a bunch of different grains that are named, and we're setting unique name based on the frame. So that's why they're changing color. So each of these grains is named, has a unique name again, which is kind of what we want for this setup. And then we're just going to emit them into the solver. So same idea, and because it's got this name, we can then go use this same setup of stripping off the everything but the library name. Whoops, I think I've got this set to the wrong thing. And so we're basically getting emitted objects. And there's actually a collision object here somewhere. Right there. So that's what it's colliding with. And same thing. You can. I think I've got videos of this. You can emit into sort of higher res. Oh, actually, I've got a couple of just to show these at kind of higher resolution. So that's just kind of higher res sand. And there's just a couple of plays through changing the attraction weight so the sand gets a little clumpier as it's going through. But if you notice, it's not sticking to the rigid bodies. So the rigid bodies have a per grain attraction weight of 0. So it's not being affected by any attraction weight. You could actually have that non-zero and have the sand stick to the rigid bodies if you wanted to, but this one has it not set up that way. And then this is the sort of similar, but just emitting into higher res sand. And again, you can see it's nice and very stable, and it's just because it's just a grain sim at the end of the day. There's no polygonal geometry here at all. It's just a way of kind of dealing with large numbers of grains. Let's see if I have everything I wanted to show on that. Yeah, so that's the basic setup. Let me show you one other reason you might do something like this. So this is, again, a very simple setup, and again, we have a unique name for all of these objects. Yeah. So all this is doing is the exact same setup as before, but actually, let me pin that. If we go into the Vellum solver, we're just doing a rest blend, right? So we're just basically deforming these points, twisting them basically through a bend, and then, But so what we get is it's deforming rigid bodies, which is kind of a contradiction, but that's what's happening here, is it's behaving like a rigid body, but its shape is changing. Because it's just a shape match, because these are just points with mass, it gets proper inertia and all that kind of stuff. And then you can do things like, actually let me re-enable all of these copies so we get more of them. And this is again just cached out. But so you can do things like, you know, point deform a bunch of boxes that are just grains inside, and they all sort of hop around and, you know, get kind of this sort of behavior that is just kind of emergent behavior from being, you know, rigid bodies, but the inertia is changing because it's just, you know, each little point that makes it up is mass. And I should say one of the reasons you do this versus a regular shape match is because all of those points actually fill the volume, you actually get better inertia. If you do a regular shape match on just a polygonal shell, it's literally a shell. You're simulating it as just like the polygonal shell, and so wherever the points happen to be on your polygonal mesh is where the mass goes, which is just not, it's not great. It doesn't look that good. So this is kind of a similar idea here. So I'm doing kind of the same thing, except I'm adding kind of a separate step, which is basically we're going to create a melted attribute, and we're going to pull it in from sort of external geometry. I'll show how that's set up in a second. And whenever a point becomes melted, we're going to clear its name, basically set its name to null, which basically means it's no longer part of a piece. It means it can collide with any grain it wants to. And then this is a bit of, there's two ways to do this. One way is to basically, we want to take any grains that are melted out of the shape match constraints. So we can either delete all the shape match constraints and recreate them from all the non-melted points and do that every frame, or this is kind of a more efficient way, but it involves some vex, so I'm just going to leave this up here. But basically what it's doing is going for every shape match constraint, looking at all of its points. If one's melted, it removes it. If all of them are melted, it removes the constraint altogether. And so what you end up getting is rigid bodies that are colliding, they're sort of deforming, they're bouncing around, and then they're basically slowly over time turning back into grains. But as they do that, the rigid bodies of grains are interacting with them, they're interacting with rigid bodies, and you get this kind of weird sort of melting-ish effect. And if we look at sort of a cached version of that, it's a little higher res. No, sorry, this one. And actually, if we, let me look at this real quick. So we're going to look at the constraint geometry here. So these are all the shape match constraints. And if we actually look at them over time, you can see the points, which this is just an attribute that holds all the points that are in the array, are changing over time, and then the shape match constraints are actually disappearing. So by the end of the sim, we just end up with a pure grain sim. So they basically just kind of melted away. And if you go up to this Vellum configure grains way up here, change this from grain to fluid, you can basically do a fluid sim and do kind of the same thing, but instead it kind of melts into fluid. So this is just a viscous fluid. So instead of melting into grains, it melts into kind of a fluidous type thing. And then you can surface this and get this kind of melting effect, which this won't play back fast enough, but so this generally looks like this. So you've got, again, rigid bodies. They're interacting with the fluid as they kind of toss it around and then kind of melting into the fluid, basically. And then just to sort of show that, you know, you can do, these are just regular, you know, vellum particles. So this is the exact same setup, but it just adds a dynamic attachment constraint. Wait, sorry, let me turn that off. So we're just basically doing the exact same setup, but we're just throwing it at a wall, putting on the attachment constraints, and then the only thing we changed about this wrangle here is it removes it from the attachment constraint and the shape match constraint as it melts. And if we look at a cached version of that, just is sort of sticking to a wall. which is, I think, this wall, yeah. And just turning it to grains, and you can see, it's very obvious here that the grains, once they become unnamed, no longer part of a piece, they're colliding with all of the other sort of rigid grains. And then you can obviously do the same thing with just changing that to fluid, and it just turns into kind of a viscous fluid pool down here at the bottom as it melts. And that just looks like this when it's surfaced. Okay, so that's kind of the rigid body tools and why you might kind of want to use them. Again, special effects, interacting with vellum geometry, that kind of thing. Oh, I think I've actually got, yeah, I forgot. This is just the same setup from before, but it's actually interacting with vellum fluid. So kind of floating around. And again, this is a little tweaky to get right, but if you want to, have vellum objects and fluid, you can do the same kind of setup. So, okay, so now let's look real quick at some constraint tools. So this is, again, stuff that existed in 19. One part of this existed in 19. So there's a very, again, sorry, chest geometry, but the idea is that you have Tommy here and you want to add a cape to him. So what we've done is actually taken the collision geometry and this just a simple grid, and we've turned the cape into cloth and then attached him to the body. And then I've cached out that setup. So I've used this Vellum IO SOP to basically write out both the geometry and the constraints. And I'm just sort of showing that this is not attached anymore. The idea is that theoretically a TD could set this up. Obviously a much more complicated and interesting example, but a TD could set up an example with a lot of constraints, and then an artist could just work with the cached out constraints, and they've already sort of got the setup here. And in 19.0, we added this thing called a constraint browser. I don't know why that's happening. Then, and it actually gives us sort of a view into, so I'm just selecting this Vellum IO, but it's showing the different constraints that are within this setup. So we've got the attached to skin and the cape setup. And so if I hit play here, I might say, okay, well that's fine, but obviously it's pinned way too, the pins aren't nearly short enough. So I can go to this attached to skin, and this is actually named based on what's called a constraint tag. So if we go back to the original setup here, this tag here, it's just OS, which means the name of the node. So I can name, if I name my vellum constraint SOPs, then they just sort of flow through to this, this constraint browser. So I can hit an edit here, and it pulls up this vellum constraint properties SOP, and it's basically this kind of weird group here basically says, chooses that constraint tag and everything that's an attached constraint. And I can say, okay, well, I want to scale my rest length down to 0.28 or something, set this to scale, and it just adds this constraint properties SOP here. And so then obviously I get a much, these guys get much shorter. And I might say, okay, that's fine, but I don't exactly like where these guys, well, and just to show it real quickly, I can do things like, if I want to change just the bend, I can do the same thing and say, okay, I want to set the stiffness to 0.1, scale it by 0.1, and now we'll have a slightly less bendy cape. And then something that is new in 19.5 is this Vellum Attach Constraints. And what this lets you do is basically import and modify the attachment constraints. So we can import all of those attachment constraints, and then when it has a sort of a tool here that we can go into the viewport and actually move these around. So if I can sort of say, okay, well, I don't really like how, because when you create the constraints, all they're doing is sort of doing the nearest point on the body. And so we might say, well, the nearest point that it came up with was actually not exactly where we want it to be. And we can sort of adjust them interactively. And we want to preserve rest length. And then when I hit play, they move to basically to those new spots, and I can do things like say, okay, I don't like the fact that it gets too close to his rear, so I'm going to go back into the tool, and I can create a couple of more attached constraints here. It just sort of properly keeps its distance. So basically just some interactive tools to kind of allow you to change some attachments and stuff while you're at it, and do things like you know, enable and disable these individual constraints that we just added. So anyway, so some interactive tools for the viewport. I keep forgetting to show my slides, but I think that gets the point across. Yeah, that was a rigid body slide, but we sort of went through all that. That was that. So fluid particles. So I just wanted to show a couple of quick sort of attributes that are relevant to vellum fluids. These are things that can mostly control how different fluids interact. So when fluids and grains interact, they act like collisions, like grain collisions. So if a fluid and a fluid or particle are interacting, they basically have an SPH, like a density, fluid density constraint between them. But if a fluid and a grain particle interact, they act like grains. They act like a hard collision. That's generally okay, but what ends up happening is you get so here I've got this blue is fluid and this is grains, and when I set it up, let's make sure we're not here. I made the density of the grains 500 and the density of the fluid 1,000. So what should happen is the grains should float up in the water or in the fluid basically. But if we hit play on this, you'll actually see what happens is this kind of, and this is, I should say this is cached. It's pretty fast, it's not this fast. The grains are actually pretty much holding back the fluid. And that's because it's a hard collision. They're basically not allowing any mixing at all. The fluid can't mix into the grains. So in vellum grains for kind of ever, there has been this attraction weight and repulsion weight. Attraction weight people use all the time to make clumpy sand. Repulsion weight is very rarely used in grains because it basically makes grain collisions softer, which for grains doesn't really make a lot of sense. You don't really want, you know, kind of soft grain collisions for the most part. But when fluid and grains interact, you actually a lot of times do want a soft collision because you want to allow mixing. So if you basically enable this, and we're setting the repulsion weight on the fluid very low, so actually when they collide, it'll take the average of that. So it'll be about half or about 0.5. And all that means is that when you do that, they'll mix essentially. So it allows the fluid and the grains to mix together, and it properly allows the grains to float on top of the fluid. So only relevant if you're doing grains and fluid together, but if you are, you get some weird collisions if you don't do this. So repulsion weight becomes important, and it's very rarely important, very rarely used otherwise, but it's actually pretty useful when you're doing fluids and grains. The other attribute is a phase attribute. So phase comes up because, so this is actually all fluid. So even though this is colored as sand, this is both of these columns of particles are vellum fluid. And when setting these up, there's this phase attribute. So phase basically indicates that that a particle is a vellum fluid particle. And if it's non-zero, it's vellum fluid, basically. So when I have two sets of fluid that have the same phase, they're considered part of the same fluid. And what that means is that when you solve things like viscosity and surface tension, you'll notice, so this is very viscous, this is not, but they stick together. And that's because viscosity and surface tension are being solved at the same time. So when phase is the same for the fluid particles, this is basically what's called a single phase fluid. So it's acting like this is maybe just a frozen part of the same fluid. So it sticks basically. If you do any FLIP simulation with viscous fluids, it sort of actually behaves the same because all of the FLIP viscosity gets solved on a background grid. So all the particle values and velocities get transferred onto the grid, solved, transferred back to the particle. So you get a lot of this same kind of mixing with the different viscosities. And then you'll also notice when the splash comes up, it sort of sticks, right? The fluid kind of sticks to the what we're calling the sand here. So if you change that phase, so you just go up here to either one of them really and change that phase to like 2, then you'll get basically what looks like like 2 separate liquids. So it doesn't stick, and it sort of throws the sand all around because it's basically acting like a different fluid, and then you'll see like when it splashes up, it looks, you know, distinct. It stays distinct because of the surface tension and viscosity are being solved separately. And I've got a couple more quick videos of that. These are just where I've actually surfaced the fluid. And so you can actually see it a little better. The fluid kind of like sort of seeps out of the sand, and it's pretty obvious that it's staying separate. I think I have a low res one of its single phase, and so you can see it's really staying on top of the particles. Just one other point about viscosity. So if you have, so we've got our viscosity set, I think it's set to 1,000 on this, yeah, which is not that high, but it's high enough that the solver has some work to do. This value right here, if you're ever doing any viscous fluids for Vellum, this spatial sort interval becomes important. And I'll show you a quick video of what that does. Basically what it means is it sorts the particles in world space, so that particles that are close together in world space are close together in memory. And that becomes very important on the GPU because, so this is just a viscous sim by itself, and what we're looking at, the visualization, is how close all the particles are together in memory. And as it mixes, so you'll sort of, this graph is showing solve time. So you can see where all the red is here. That basically means that you have points that are far apart in memory that are close together in world space, and solve time goes way up. And then we're going to sort, and you see it goes way back down. So basically all the red goes away, the solve time goes way back down. So we're sorting basically in memory to, because all of these particles have to look at their neighbors. And if their neighbors are very close in memory, that's fast on the GPU. If their neighbors are very far away in memory, it gets pretty slow. So basically we're resorting every, in that case, in that sim, I was doing every 5 frames. The default is 20, but this actually defaults to off because it changes the point numbers, which is weird. So the point numbers that come out are not consistent. And that just doesn't happen in any other part of Vellum. So it's strange enough that we default it to off. But if you're doing any sort of viscous fluid sims, you should really turn this on. Okay, so we have time for a couple of stupid Vellum tricks. These are just things that people have kind of asked me that turns out they happen to be hair related, which we haven't really talked about yet, so I guess that's good. So somebody said, I want to do like a squish, like a fuzzy ball, let's say. What am I trying to think? Yeah, sure, a pom-pom, squish ball, whatever they're called. And so he had his tetrahedral ball here, and he had a bunch of hair that he had created onto this original sphere. And then he sort of packed them up and unpacked them together. And then he used a stitch constraint to attach the hair to the tetrahedral ball. And because he wanted them to solve at the same time, and he'd play, and all of the things fell off. Now, if you'll see, they are solving together, right? Like the hair bounces off the ball, but it's not connected. So the first sort of weird thing about that needs to be done is that this stitch constraint, he had it attached to the tetrahedral body, but stitch constraints only work with, especially when this closest locational primitive, they only work with triangles. So we need to go up to the tet conform, the thing that created all the tetrahedra, and add surface triangles, and then we will get we'll get a new group called surface triangles, and now it'll stick. So that's fine, but if you notice, it's not like we're not preserving the orientation of the hairs here. They're just sort of collapsing onto the ball. So this doesn't really give us the look that we want. So the traditional way of doing this is actually as 2 simulations. So you start off and you do it with, you just simulate the soft body. And then you take that and you point deform the original skin. So this is the skin that we graded the hair from in the first place. And then you basically create a bunch of pins on the guides, and we leave this, this match animation on, and we've got, so we're basically we've got orientation pins on the hair, and then we're doing a guide deform. And so what guide deform will do is it will actually take that soft body simulation and deform the guides to basically match it. So it's updating the orientation of these hairs, their position, all that kind of stuff. It's not simulating the hairs, it's just deforming them. And then because this match animation is on, when the solver is running, it will actually copy that input orientation onto those pins. And so what we get is a simulation that looks kind of what you would expect. You would get these orientations updated correctly. Now the problem is this is no longer a coupled sim. And what that means is if we go and add a bunch of pins here, so we're just going to sort of pin a bunch of these points. Basically, we can't stop the ball, right? So the hair can't affect the ball in any way. So it just sort of goes about its business because they're two separate sims. If we go back to this coupled one, even though it looks wrong, it snaps back, right? So the hair is affecting the ball here. So the question was just, can we do both at the same time? And so what we're actually going to do here is we're going to create a bunch of those same pins, but we're going to actually get rid of the one that constrains the position of the hairs. And then we're going to run the same thing that we did. Sorry, I got to go remove those pins. Sorry. So we're going to do the same thing that we did, but we're going to do it in the SOP solver, which is just kind of one of those weird Houdini things you can do. So we've got this SOP solver here. We're actually operating on the constraint geometry. So these are all the geometry that represents the constraints. And we basically just move that set of SOP controls into this SOP solver. So we're doing the same thing. We're point deforming that original skin. We're taking in the original simulation geometry and guide deforming it. And then we're just manually updating the rest vector, which is on those pin orient constraints. So essentially, we are doing what the solver would normally do, but we're doing it ourselves. And so what we get is a coupled simulation where the orientation gets updated. And you can just sort of prove that by, I don't know if we really need to do it, but if you go back to the hair and pin some points, you sort of get, you get an orientation, but you also get a coupled simulation where the hair actually affects the soft body. So, sort of a quick similar idea is people do this kind of like things where they'll do like flowers and stuff where they use kin effects. And somebody was just asking, well, how do you do this as a straight vellum sim? So this is just a bunch of hair that basically gets, its bend updated over time and then just sort of drops to the ground. And all we're doing here is we're using a vellum constraint property on the bend twist constraints, which are in the hair here. And we're doing the same thing, just updating the rest vector, which is the orientation of those. And we're using this update rest vector orient. So this is very kind of advanced, but the main thing I wanted to show here is that you can actually just update the angles that are on the hair constraints directly. And it looks at this pbd constraints.h file, which is actually included in Houdini. This is a huge file. It's all vex that I would, if you're sort of an advanced TD level person, I would look at a lot of this stuff because, for instance, basically all the constraint generation, all the rest updates, all the sort of constraint manipulation that happens in vex is all in here. So it's actually this update rest vector orient function is in here, right here. And that's what it's doing, is it's just calling that. This is actually sort of interesting because the same thing is happening that we were looking at before. If we undo this fuse real quick, and we're going to visualize our pins, we have the same thing where the pins are sticking around. So the reason that these things stay standing up is because they're still pinned. They still have an orientation pin on them, even though they're no longer joined together because we got rid of that fuse. And if we just add a quick thing to delete those pin orientations as well, then we'll get this kind of thing where they just sort of fall apart. We don't really show it, but you can brush these. I mean, this is all very fast and kind of just an interesting little guide. You could also do this by, deforming the wires with like KinEffects and doing a rest blend, but just sort of an interesting way to affect the angle of the hair directly. And then finally, this is something that somebody asked about where they wanted to do some procedural hair brushing. And so the idea here is, let me change the background. I'll just play it for a second so you can sort of see what's happening. So this looks sort of like Vellum Brush, but it isn't. So this is basically, we just created a little stroke tool, actually Jeff Late did. And all it does is it lets you draw while the play bar is playing, and it just stamps the time onto these curves. So every point gets a time. And then what this is doing is within the Vellum solver, it's actually reading, this is kind of another complicated wrangle, but it's basically reading that point, looking at the start frame and saying if this brush stroke basically should be applied at this frame, then this code here is just kind of like making a little brush out of it. But what's kind of an interesting setup is, so we want to say, okay, let's say we want to just have this brush first affect the sort of right half of the hair. And one of the nice things about Vellum is everything that comes out of here, the constraints in the solve, can then be fed into another solver. So all we're doing is time shifting. So we're taking the sort of 240th frame of this, then we're pinning this right side and unpinning this left side and removing all the velocity from the blue. So the blue gets pinned, left gets unpinned, and then we're just running it again. And so now all those we've got the pre-brushed part here, and all the left side here is basically brushing itself. And then we do the same thing. We unpin everything and do a final drape just to kind of get the final hairstyle that we're going to look at. And I should say that one other thing we've got in here is a Vellum rest blend that's basically just using the simulation geometry. So it's basically saying whenever you brush the hair in a particular direction, stay there. That becomes a new rest state. So basically, accept those angles of the hairs as the new state. So it basically is like if you had sort of hairspray or something in there. And I think I can probably show that brushing in real time. So if we go to this and clear the brush strokes, hit play. So this is, we're just basically recording these brush strokes in the, and then, next time you play back, you'll be getting that version of the new strokes. So just sort of an interesting way to do kind of like procedural hair brushing and sort of a different, if you wanted to do a bunch of different steps in creating some sort of procedural groove. So that's all I have. We have a few minutes for questions, like 5. If you guys have any, I'll also be around afterwards if you want to come find me and ask questions. Are there any questions?
Anyone? Oh, we can pass the mic just so that we can record this.
Can I ask from here? So just a general question about the examples that you were showing. If we want to request for a demo, do you just submit this to the forum, or is there?
Yeah, we're gonna. All these are recorded, right? And so we'll just somehow make these files available.
Associated with the downloads.
Oh, I meant like if there is any new request for, because we are pretty new with like working with Vellum hair, and I was just wondering if there is something we run into while we're working, and if we want to make a new request, do you usually just submit it to the forum?
Generally, support is generally the best place to ask questions, because they will route them to the proper person, which is usually me. But I don't always follow everything that's on the forum. There's just a lot of traffic, so probably the best place is support. There are a lot of people on the forum, so if it's a question you think a bunch of people have probably had before, the forum's a good place to start. But if it's a very, some of the stuff that is very technical about, well, how do you do these kind of weird things that people haven't really tried before, then just put them on support and they'll get to me, okay. Most likely.
Thank you.
Yeah.
Anyone else? No one, silence. Okay, that's it. No, seriously, no questions? Yeah, we good to go? Yeah. This is
Hi. Just actually, it occurred to me with when you did the fluid, the vellum fluid colliding with grains. If you relax that repulsion weight on the fluid, does it become splashier, and is there ways to kind
No, the repulsion weight only affects when it is colliding with grains.
Okay.
So the viscosity is really the control for that.
Okay, cool.
But if you set repulsion weight on a fluid sim that doesn't have any grains at all, it won't do anything.
Okay, great.
It's just when it is interacting with grains. So it's a pretty specific case. It's just obscure enough. I wanted to point it out because people probably will not figure that out.
Okay, awesome.
By default. I think there's another one beyond
Is
over
there
here.
another one? Okay.
Oh, stand up. Okay. Sure.
Hi, John. I don't want to get into the very depth of it, but it's just about a shot that we were trying to do is where we were having difficulties with rotations with hair. Mm-hmm. And as you mentioned about match to animation, which takes the orientation in consideration. Is that something that acts as a goal, or is it just takes the orientation into account?
It depends on whether you do, so when you create the pin, you can either specify it as a soft pin or a hard pin. If it's a hard pin, then it just sets the orientation of that point. If it is a soft pin, then it is more of a goal, and it's according to the stiffness of that pin constraint. One thing that and I wanted to show that is, and let me see if I can get back to it really quickly. That was this one that some people don't do, and we probably honestly should be more clear about this, is you really want to do the guide deform after you've created your pins. So what time, and after you've created your hair constraints. So sometimes what people will do is they'll deform the hair, and then they'll create hair constraints afterwards, and the hair constraints will recompute the orientation. We try to do a good job of that, but because you don't have a stable basis there, you can sometimes get some flipping and stuff. Whereas guide deform, because it's got the skin underneath it, does a better job of keeping that stable basis. So generally the way you want to do it is create the hair, create your pins, and then just guide deform at the very end right before you go into the solver. And honestly, I don't think we do a good enough job of making that clear that that's really the best way to do it, because you're most likely to have stable orientations as the hair deforms. I mean, as the skin deforms.
It was on.
Yeah.
Yeah, one more? Yeah.
Same question. I think one of the reasons why a lot of people do the deform and then the solver, I think it's like the default setup is like you have the guide groom, guide deform, and then the guide sim, and you have like constraints created in the sim after the guide deform. So I think that's how most people kind of follow that approach.
I think you're right, and I think that we probably need to fix that, because I mean, again, we do a decent job of that, but it is because you only have the hairs, you don't have the skin. When you're recomputing the constraints, like Vellum constraints doesn't know anything about the skin, and so guide deformed really does a better job. And so it's possible we need to revisit that workflow, because this really is the better way to do it. And that may
It's good to know, because then we can revise our
Yeah.
setups in that way.
Thanks. So if nobody else has any questions, then we'll wrap up this talk. And I suggest that you guys head on over across the other side to get a shirt and some foam toys.